Welcome. In this lecture in linear data analysis, which has multiple sessions, we'll begin our exploration of the singular value decomposition. The main concepts for this lecture are we'll explore a matrix and its transpose, and there are two ways to take this product. These two different products will lead us to what we will call left and right singular vectors. It will turn out that the ways of taking the transpose have shared eigenvalues. This will lead us to the singular value decomposition, which is most commonly known as the SVD. This is perhaps the most important theorem in linear algebra that was developed in the 20th century. One problem that we can think of as we go through this lecture are what could eigenvalue mean if a matrix is not square? What sort of thing is this? What kind of generalization could we have? So let's begin by recalling a diagonalizable matrix. Suppose that we have a matrix that's square and it has an eigenvector basis. That is, the eigenvectors are linearly independent. This means that we can write the matrix as the eigenvectors collected into an eigenvector matrix times a diagonal matrix with the eigenvalues times the inverse of the eigenvector basis. Suppose that we have a general matrix. This matrix may or may not be square. What happens if the matrix is square and full rank but doesn't have an eigenvector basis? This can happen, for example, with certain matrices where there are repeated eigenvalues. What if the matrix is square and rank deficient? That is, what if the null space is quite non-trivial? That would be an example of where the repeated eigenvalues are specifically the value 0. What do we do if the matrix is rectangular and full rank? And what could we do if the matrix is rectangular and rank deficient? These are all cases that we'll learn to handle in this lecture. So the method that we'll use is, in this lecture, what we're going to do is we're going to examine two particular matrices. One is we'll take a matrix and pre-multiply it by its transpose. We already know that if this matrix is tall thin, that is, if it's full rank and there are more rows than columns, then that's symmetric positive definite, and in general this is symmetric positive semi-definite, and it's diagonalizable. What we can understand, although we haven't explored it in any detail, is that if we take the transpose product in the other way, if we multiply the matrix by its transpose, that is also a symmetric positive semi-definite matrix. It's diagonalizable. One of the key insights for us is these matrices have eigenvalues in common.